Hello everyone, this is Wilson from University of Illinois at Urbana-Champaign. Today, I want to present our work, EScALation, a framework for efficient and scalable spatial-temporal action localization. Nowadays, cameras are playing an important role in our life. For example, in smart homes, cameras are used to monitor the house and notify the house owner if there is any suspicious activities. In autonomous driving cars, the system analyzes the road situation through the camera in order to navigate the car. Obviously, cameras help us understand the environments and make our life better. Mostly, computer vision algorithms apply to analyze these videos, specifically to enable autonomous analysis of videos. Spatial-temporal action localization or action detection has been proposed. Action detection aims at finding sequences of bounding boxes associated with an action. We call this action 2, an action class in the video. For example, biking, ice dancing, walking dog. The figures below show example 3 action classes. The first row represents the action of child biking. The second row represents action of ice dancing. Note that here we have one action class on the second row, but 2 action tubes. One is associated with the man, the other is associated with the woman. The last row represents the action of walking dog. Action detection is challenging because it involves finding the spatial information and temporal information. Spatial information means the algorithm need to locate the bounding boxes. Temporal information means the algorithm need to determine the start and the end time of an action tube. Though there have been approaches proposed to address these challenges, there are still existing problems. One problem is that current existing approaches, they apply per frame bounding box detection based on CNN, which is quite resource intensive. The other problem is that existing tube linking approaches does not scale well to a large number of action classes. We did some experiments to compare the backbone network, hardware, speed, and MAP, which is it represents the accuracy of action detection of different approaches on the dataset UCF124. We find that although the accuracy is improving from 32.1% to 48.8%, high-end GPUs are needed for like NVIDIA Titan X, NVIDIA Titan XP to achieve a real-time speed of nearly 30 frames per second. So how can we mitigate these existing problems? Fortunately, when we look at the bounding box detection results in action detection, we find that the bounding boxes of neighboring frames, they are actually quite similar. Like in this example, the green bounding boxes represent the correct action detection, while the red bounding box represent the incorrect bounding box detection. We find the green bounding boxes in neighboring frames, their location is quite similar. What if we skip the processing of certain frames that are similar to its neighboring ones and use the result of neighboring frames to represent the skip the frames? In other words, The temporal correlation in the video can be utilized in action detection to remove redundant computation. Based on this intuition, we propose EScALation, a novel framework for optimizing action detection in videos. It overcomes the resource-intensive problem of existing bounding box detection networks and makes tube linking scalable by taking advantage of the temporal correlation in video. Before introducing EScALation, let's first have an understanding of how the state-of-the-art action detection approach UVO works. Basically, UVO involves two steps. One is bounding box detection that is applied to all frames. The other is tube linking that is applied to all classes. The input to the pipeline is a sequence of RGB frames. The bounding box detection network generates bounding box information from the input. The bounding box information is then processed by tube linking, which attempts to generate action tubes for all classes. Now let's look at the pipeline of EScALation. In contrast to the previous pipeline, EScALation mainly involves two strategies. One is frame sampling, the other is class filtering. So look at this pipeline. The input to the pipeline is a sequence of RGB frames. The frame sampling technique skips a subset of input frames and produces the sample frames. And in this example, we sample one frame in every 3 frames. We define the sampling interval as the number of skipped frames between 2 consecutively sampled frames as the sampling interval. So in this example, the sampling interval is 2. Then the skipped frames will be processed by the bounding box detection network, and the results will be copied to the frames that are skipped. After that, the bounding box information will be processed by tube linking with class filtering. Basically, the system will predict the action class represented by the blue color, and then tube linking will be performed only on the predicted class. And finally, we can generate the action tube. The key to success is a strategy to sample frames and predict classes. Next, we will talk about frame sampling and the class filtering in more detail. So for frame sampling, our strategy is to slice the video into multiple sequences of frames of the same length. Apply CNN to the first frame and skip the rest frames in every sequence. So in this example, we have a sequence of 5 frames. Without sampling, all of those 5 frames will be processed by CNN. But with filtering, with frame sampling, only the first frame will be processed by CNN, while the rest will be skipped. To show why this strategy works, we choose different IOU thresholds. The IOU threshold is the threshold determining whether a detected bounding box is correct based on the intersection of a union. Basically, a smaller IOU threshold, like 0.05, means more likely detected bounding box is correct. And we change the sampling interval from 0 to 29. So 0 means no frames will be skipped. And we apply this strategy to UVO on the training set of the UCF 134 dataset. And the 2 figures shows the result. The figure on the left shows how the MAP changes with the sampling interval, while the right figure shows how the action detection time changes with the sampling interval. We find the MAP of UVO with sampling does not change too much as the sampling interval increases. especially for low IOU thresholds. While the time of action detection drops fast as the sampling interval increases. This environment implies that the MAP is less affected while the action detection time is significantly reduced by frame sampling. The only problem is how to determine the optimal sampling interval. To find the optimal sampling interval, we need to first define what is the optimal sampling interval. To do this, we introduce a new action detection metric called action localization score. It quantifies the quality of action localization based on both time and accuracy. It's defined in this equation. Well, MAP is the mean average precision. T is the average action localization time per video on a dataset. M and N are constant positive integers characterizing the significance of MAP and T. Basically, a higher value of M means a higher importance of the MAP, while a higher value of N means a lower importance of the action localization time. So basically, the sampling interval, the optimal sampling interval is the interval that maximizes the action localization score. And to find such a sampling interval, a hypothesis is that the action localization score on the test set should respond to the sampling interval like on the training set. The intuition is that if the video in the training set favors large sampling intervals because the content in the video is slow changing, then large sampling intervals should also work well on videos in the test set, which contains almost the same or contains a similar video as in the training set. So we did experiments comparing the different curves, including the MAP versus the sampling interval, the action localization time versus sampling interval, and most importantly, the action localization score versus the sampling interval. We find that all these curves look similar on either the training set or the test set. So this means we can choose the sampling interval that maximizes the action localization score on the training set. Then we apply the derived sampling interval on the test set. And this is how the sampling interval will be selected. For class filtering, it predicts the action class in the video in a lightweight manner before tube linking. Filter out all other classes and only links tubes of the predicted class. The prediction is made based on the class-specific score average over different classes in the first keyframes of a video. And this figure shows the relationship between the accuracy and the number of reference frames. We notice that the accuracy on both datasets reaches a plateau when k is around 30 after video is being played for 1 second. And the accuracy is over 90 and 80% respectively. For like evaluation, we compared our approach against the baseline approach lower. For the datasets, we choose UCFR 124 and the JHMDB21. We conduct an experiment on Linux desktop with 2 RTX 2080 Ti GPUs. For the metrics, we use the action localization score, and we set the different values of M and N to create 2 scenarios. The first scenario focuses more on the MAP, while the second scenario focuses more on the detection time. And here's the overall action detection result on UCL 101-24. In scenario 1, the action localization time is reduced by about 70% with 6.1% loss of MAP. And the action localization score improvement is about 24.6%. Result on the second scenario is similar with more reduction in the action localization time. And this is the result on GHMDB21. The action localization time saved by also nearly 70% with 10% loss of MAP, and the action localization score improvement of 6.1%. And similar result on scenario 2. In conclusion, we present EScALation, a framework for efficient and scalable spatial-temporal action localization, which mainly involves frame sampling and class filtering. Our evaluation using UCF 124 and GHMDB21 demonstrates that EScALation can greatly reduce the action detection time and state-of-the-art approach UVO with only a slight loss of the MAP, which improves the action localization score. In the future, we will adapt the frame sampling interval based on processor frames to further improve the accuracy time trade-offs. We can also integrate frame sampling and image compression techniques to reduce the size of video to be transmitted in an end-to-end action detection system. This is the end of the presentation.